All right, well, it is now noon. This is Amy Guerin, Director of Brand and Digital Strategy with AOCS. And thank you, everyone, for joining us for today's Webinar Wednesday. And we will be hearing about rheology from Mark Patrick with Rheology Testing Service. Mark is the founder of Rheology Testing Services located in North Carolina, USA. He has a PhD in medicinal chemistry from the University of North Carolina, Chapel Hill, and served as team manager, consultant, and mentor over 30 years in early pharmaceutical development with 24 at GlaxoSmithKline. Mark's technical focus was new chemical entity properties optimization along with formulation development. While at Stiefel, a dermatology subsidiary of GSK, Mark became the rheometer lead user and trainer. It quickly became apparent to Mark that there is a general lack of understanding and appreciation for the potential of rheology to provide insight into formulation development and product manufacturing issues. Much more than just viscosity. When the opportunity arose, Mark founded Rheology Testing Services. Mark welcomes the opportunity to apply an array of rheology assays that may provide insight to better understand your processes and products. And so now I'll turn it over to Mark for rheology principles and applications.
Okay, great. Thanks, Amy. I want to thank AOCS for the opportunity to present this webinar and also you, the audience, for your time. The goal of this presentation is to provide an overview of rheology to give you an appreciation for what it can do. I'll talk about an array of assays and applications, and as Amy noted, it's much more than viscosity. So rheology can be applied from the earliest stages of research and development all the way through the manufacture of marketed products that can support the biopharmaceutical, pharmaceutical engineering, bioengineering, food, cosmetic, and other industries. And along those lines, it can be very helpful to provide insight for product development, optimization, including quality by design, which is known as QBD. Can be involved with exploring various aspects of manufacturing optimization and in-process control, as well as physical stability, delivery, performance efficacy, sensory attributes such as does it feel sticky, is it creamy, does it smooth on easily, as well as regulatory considerations to evaluate the macrostructure equivalence, known as Q3, as well as various aspects of support for biotechnology. So before we get into principles and applications, I'd like to just take a minute or two to talk about the rheometer overall. As we can see, there is the upper plate and the lower plate. The upper plate is the only moving part that actually contacts the sample. It can be smooth, rough, or serrated. And the lower plate does not move. It is usually the same surface as the upper plate, and it is exquisitely temperature controlled. So if we kind of move further out now, this at least it connects this rheometer from Malvern. The upper plate actually has three movements. It can be rotational, you see in the green curve, and just going in one direction. It could be oscillational, bidirectional, and that could be kind of analogous to the agitator in a washing machine. And then we have a vertical movement, which is used for the evaluation of stickiness. So by the end of the presentation, hopefully you will have a better appreciation of what assay I should use to address a particular question to drive the project to meet the business needs, and what experimental parameters should I consider. And also, you know, just as when you're out with your friends and at a party or whatever, you can have a great conversation about what is more viscous, honey or mayonnaise, or is silly putty a viscoelastic solid or liquid? So there, just want to go through the basic menu of assays. And we need to keep in mind that when people tend to mention rheology, people just immediately go to viscosity and that's it. But actually, the science and field of rheology is much larger. And hopefully I'll give you a better appreciation of that as we go through this webinar today. The viscometer is a very good basic QC instrument. It can see if the batches are generally similar, if they've changed over time, and so on. It generates a single value at defined temperature, spindle type, and speed. A rheometer characterizes the sample in much more detail, using rotational, oscillational, and vertical movements. And we will talk about each of these various assays. Well, with the non-equilibrium ramp viscosity measurement, and compare that with doing an equilibrium or step viscosity. We'll also talk about thixotropy, creep test, and temperature sweep. And then we'll move on to oscillational mode of studies that involve amplitude, frequency, and temperature sweeps. And then we'll wrap up the assay set with a pull wave description. Okay, the regulatory expectation is involved with Q3. So we'll talk about Q1, 2, 3. Q1, just to back up here, is there is a regulatory expectation that you were to demonstrate that the product is similar to the reference listed drug, the RLD, or an AND. That's an abbreviated new drug application that's required for the FDA or by the FDA for a generic company to market its pharmaceutical product. So the Q1 is qualitative. Okay, we can say it has the same components. Q2 also the same components in the same amount. And Q3 involves the microstructure. So that's Q1 and Q2 elements. And then we add the arrangement of matter. We have to demonstrate that the material has the same arrangement of matter. So if we look at the schematic, molecules of some sort, we can see that under different conditions, in this case, increasing concentration, we can have spherical, log-like, worm-like arrangements. And each of these arrangements can affect its biological activity or whatever other properties we're trying to leverage. A rheometer is capable of discerning among many of these arrangements. So we do need to focus on viscosity. So viscosity is basically just the resistance to flow. So if we look here in the bottom right-hand corner, we can see this person, he's pushing this truck. He's applying stress, and the more stress he puts on trying to push the truck, the more displacement the truck will move over time. And so it's the same thing, very similar with the rheometer. So the rheometer measures the push or the stress needed to get the material to move a certain speed, or known as shear rate, and vice versa. So let's focus on this a little bit more. So we have the sample here in green in between the upper and the lower plate. The top plate will rotate at whatever setting we set the rheometer at, and supplying a force across an area of the plate to the sample and through the sample. So I promise you there's not going to be much math in this webinar. So viscosity is shear stress over shear rate. So if we break that down, it's actually the force that the upper plate is applying over the area of the upper plate over the strain over time, which is shear rate. So, and the strain is defined as the displacement over height. So this is the displacement in the horizontal displacement versus the height. And that is defined by the gap distance between the two plates. And so it's also very much analogous to the stack of cards. When perfectly stacked is right before the assay, and then the upper plate will move and it will shift the sample in a particular way. However, I do want to point out that in this particular stack, we have a problem with these cards that are shifted a little bit. And we're going to talk about that in a few minutes. That's a rheological problem that we need to consider. So rheologically, most samples can be broken down into Newtonian and non-Newtonian. In the case of a Newtonian sample, as the shear rate is increased, viscosity remains the same. Typical examples are silicone oil, which we use as our rheological standard often, as well as water. Non-Newtonian samples will have a response based on a change in the shear rate. So most samples that we typically encounter will shear thin as the shear rate increases. They could be lotions, creams, ointments, and so on. There are some materials that do thicken as the shear rate increases, and a classic example is corn starch. And there's some really fun videos on YouTube where people made these pools of cornstarch with water, and you can actually run across it, and it will support your weight. However, if you stop, you will sink. And so this situation there is when you're running, you're applying a force that's a high shear rate, it can support your weight. As soon as you stop, the shear rate goes down, it can no longer support your weight, and you sink. This kind of study, and we'll talk about flow curves in more detail in a minute, is helpful to model processes such as spreading, pumping, frangibility, and feel. So, I've been using the term shear rate. Well, what do these numbers mean? What does this mean? And so, in this particular curve, we can see that at very low shear rates, we're talking about micro to milli reciprocal seconds. That represents storage and sedimentation, or the process of, say, icing on a cake starting to sag. And this can go all the way down to over a range of 1 trillion to processes that involve spraying, and that could be up to 1 million reciprocal seconds. It's also very noteworthy to know that a viscometer, rotational rheometer, and a capillary rheometer have various ranges in which they're most capable. You see, the rotational rheometer has a range that covers most of the rheological assay needs. Let's focus in on some shear rates of some common processes that we typically encounter, and we'll use cream as our model. So, in this particular case, a hand cream in a jar might experience a shear rate, very low shear rate, of around 1 milli reciprocal second. As we go into sample delivery, such as scooping it or pumping it, that might be 10 reciprocal seconds. We're just kind of gently spreading on the hand, maybe 1 reciprocal second. And then if we're aggressively rubbing something into, say, our hand, that would be a higher shear rate, representing around 100 reciprocal seconds. And that's where you can get a sense: is this thick? Is it hard to spread? So we'll talk about this in more detail. So let's focus even more closely here on the effect of shear on microstructure. And so we have 4 models here. So at rest, samples of material may be an entangled mesh. It may have some droplets, like emulsion droplets, oil droplets, elongated particles such as needles or rods, and some materials may cluster as aggregates. Once we start applying a particular shear, a polymer chain may disentangle and stretch. The droplets may reorganize into forms that aligns with the flow of the shear rate, or the direction of the shear rate vector. The particles may also become elongated, and the aggregates may break down into primary particulates, or if they're small chains, the smaller chains will align with the direction of the shear. So let's get into some actual shear stress flow curve plots here. And this is a non-equilibrium ramp. In this case, we're looking at a product that is undergoing increasing shear stress. As you see, as we're increasing our shear stress in a linear ramp mode, there's elastic deformation. The stress will increase until a certain point at which we have now overcome the energies of the material to hold itself together, and it literally breaks. The material will begin to flow, and the viscosity we see will drop very sharply. At this point, this is the yield stress point, at which we report the yield viscosity as well as the yield stress. There's some experimental considerations to keep in mind here. Do we use a cone or plate? Do we use a smooth cone or smooth geometry, rough or serrated? Also, what kind of ramp rate should we be using? And I'm just using a rubber band as an example in this case. Well, if we go with a very low or slow stress rate, we're just slowly stretching the rubber band. And that certainly models one type of process. However, we may be interested in investigating a high shear process at a fast rate. And so if we have a sharper ramp, we can end up snapping breaking the rubber band if it's fast enough and hard enough. Okay, this is a flow curve of two catch-up samples. Brand 1, brand 2, these are just right out of the store. And you see this is before we see an elastic deformation as the stress is increasing, and then at some point we've overcome the structure of the product and the viscosity drops. We've gone past the yield stress. You can see that brand 2 in red has a higher yield stress, higher viscosity than brand 1. So the other thing we should be thinking about, well, we've broken the structure and it's flowing. Well, we'll rebuild once we take away the stress. This is very similar to, if you do have your, say, ketchup, this is a great example for this process. If you take your ketchup in a bottle and turn upside down, most of the times it won't flow. You kind of have to hit the bottle for it to flow. And that process, you're applying a force or a stress to the material that causes it to liquefy, and then it will flow out into your hamburger or French fries. However, we don't want it to just flow off the hamburger or flow through the French fries. We want it to stay. So that's another study we'll talk about. This particular study, flow curve yield stress study, can model if the sample is likely to settle, and that can be applied by something like Stokes' law, in which you can determine can the downward force of the particle overcome the yield stress of your formulation. If the downward force is greater than the yield stress of your formulation, then they can tend to settle. If it's less than, then it has a greater tendency to not settle. And of course, there's other parameters involved with this, but that's just at least one way of looking at your material. To model if the material has difficulty starting to pump or stir, you can be involved with formulation optimization as well as manufacturing optimization. It also gives some insight into how a customer may feel about the various materials, the thicker, creamier, and so on. Okay, that first study was a non-equilibrium type of study. The other kind of study is an equilibrium or shear rate depth study. And in this case, we have the sample in between the plates, and they're experiencing a shear rate. And as they experience a shear rate, it will, this one shear rate, it's not a ramp, it's a set shear rate, this particular sample will shear thin until it reaches a particular equilibrium. These conditions and criteria are defined within the method that I would write. Once that is established, then it goes on to the next step, increases the shear rate to the next step, you get additional shear thickening, or shear thinning in this case. And then once equilibrium is established, then go to the next step. And this could go for many stages. So the output of this is a curve that something like this is typical of solid. At a very low shear rate, a solid can have infinite viscosity, whereas a liquid will have a different curve that could have a zero shear viscosity until you reach a certain shear, and then we'll start to shear thin. I want to talk about some experimental considerations, and one is being mindful about the slippage at the plate sample interface. You may recall that we were talking about this deck of cards, and there was I mentioned that the top several cards were shifted from the rest of the deck. This is an analogy to slippage in our sample between the rheometer plates. And this is often seen where if you have slippage on this shear stress versus viscosity plot, you'll see this kind of a sudden shift in your viscosity, versus if you don't have slippage, it's kind of a nice, more smooth effect. And what's going on here is, ideally, when you don't have slippage, you want this top plate imparting force through the sample from the top plate to the bottom plate. That's the ideal. In the case of slipping, though, the top plate is only interacting with the top part of the sample, as we see here in this deck of cards. Only these top several cards that have moved. The rest of the deck hasn't really moved in relationship to the top card. One way to remedy this and to investigate this is if you suspect slippage and you're using something like a smooth plate, switch to a rough or serrated plate that is able to grab the sample and then impart its energy or force through the sample. And you should, if you are getting slippage, you should get a change in the curve from something like this to something more smooth as in this upper curve. And it's important to note that it would make sense that if you're getting slippage, this could result in very significant experimental error. And I want to take a few minutes here and talk about some other experimental considerations. Consistency is critical. How you load the sample onto the rheometer is critical. Even in the process of transferring sample to the rheometer plate, you are adding shear to that sample. And that sample may be sensitive to that. You could also be introducing some bubbles, which can also greatly affect your results. You need to be mindful about consistent trimming to remove the excess sample. Once you apply the sample, the top plate comes down, compresses the sample, it sends some sample out on the side, and you need to trim that, and it needs to be consistent and well done. You need to think about the geometry, and that's the term that corresponds to do we use a cone, do we use a plate, cup and bob, and there's a whole range of other accessories that can be used on both the rheometer and a viscometer. For the purposes of this webinar, I'm only going to focus on cone and plate. Cone gives more consistent shear across the sample, and it gives a little bit percentage better accuracy. And so what's happening here is the sample that's right in the middle of a, in this case, parallel plate, that's experiencing a lower shear than the sample that's further out when that plate is moving in one way or another. And so using a cone, that helps to give a better shear across the radius of the plate, or the cone in this case. A cone is not recommended for temperature sweeps if it's not if there's no compensation for thermal expansion. The size of the plate and cone is also very important. The larger diameter geometry is better for a less viscous sample. You're working with a larger surface area. However, it does require a larger sample. Other experimental considerations are, again, consistency is critical. I know I'm repeating this because it is very critical. We also need to think about the plate cone gap. Typically, I like to work around 0.2 to 1 millimeters, and it depends on the kind of sample. A smaller gap requires less sample. Sometimes the client just doesn't have much sample to spare. For example, a 200 micron gap with a 25 millimeter plate requires 140 microliters to fill a gap. But really, I like to have at least 200 microliters to work with. A smaller gap provides a higher shear, and that's because the shear rate is strain over time, and strain is displacement over height. So if the height is smaller, we have a higher strain, or a higher strain, which gives us a higher shear. It also reduces the potential to lose sample from the gap at a high shear rate. And also, we also need to be mindful though that a smaller gap is more sensitive to the gap in accuracy. If we have a gap of, say, an accuracy of just 2 microns, that's 1% of a 0.2 millimeter gap versus it's a much smaller percentage error for a 1 millimeter gap. There's also the 1/10 rule, where the gap should be at least 10 times that of the largest particle or droplet size. And to put this in perspective, the default gap for a cone is about 150 microns. And so if you're going to use a cone, the largest particle or droplet should be no more than 15 microns. You can also set the gap based on height, which is typical for most of the samples. However, sometimes I'll get some polymeric samples that may have inconsistent thickness from batch to batch and sample to sample. And so this is where you can apply a force. You can say, okay, I'm going to apply a 0.11 or even up to 40 Newton force. And so that you have a consistent force on your sample, and then you can do your measurements with more confidence to compare from sample to sample. And the rheometer will accurately, in many decimal places, track the sample height or thickness through the assay, depending on whatever that force is. Okay, the last set of experimental considerations is to pre-shear or not to pre-shear? That depends on the question to be answered. And what I mean by that is in the process of adding a sample to the rheometer, you may be imparting some shear, and that may rheologically change your sample. So you want to pre-shear, you may want to consider pre-shearing your sample, typically in the opposite direction, very low shear, just to kind of normalize your sample, and then you can begin your assays from there. It kind of gives all the samples kind of at the same starting point. But we need to be mindful that we don't want to erase some other rheological properties, especially if the sample really easily shear thin and it has very poor rebuilding. The sample may change over time during handling and analysis. And I have some studies that run overnight, a good many hours, as the sample curing, is it degrading, is it rebuilding and crossing, is it losing volatile? So we won't perform a single frequency sweep and monitor the G prime, which is the elastic modulus, if that changes. You may ask, well, what's a G prime? Well, stay tuned, we'll talk about that. By the end of this, you'll have a much better idea. Also, if you have volatile, you want to use the solvent trap. So it maintains the sample in an environment in which the sample environment is saturated with that particular volatile mixture. Also, some samples are sensitive to oxidation at elevated temperature. I just wrapped up a study a few weeks ago looking at polymeric material at 180 degrees C, and it had to be, and there was concern about oxidation. So I was able to, I have a setup that I can keep a very low nitrogen flow over that sample all time. And it's an enclosed, sealed environment around that sample. Okay, so with these experimental considerations in mind, I'm going to move on to other assays. Thixotropy is a typically a three-step rotational shear study, and this determines the rebuild extent and rate after high shear. And we'll use ketchup again, as this is a great model for this. Again, we have the same two brands that we talked about earlier. We're looking at 3 steps. In step 1, it's a low shear. In this case, it's a 1 milli reciprocal second, 0.001 reciprocal second. And we see that the red, brand 2 ketchup has a much higher viscosity than brand 1 in blue. However, when we apply a high shear, about 10 reciprocal seconds, again, that's not really that much. You see that the viscosity drops very quickly and to very low values. However, once we take that higher shear off and go back to our baseline shear of 1 milli reciprocal second, you see that both ketchups rebuild very quickly. It's interesting to note that the brand 2 here in red does not rebuild to the same extent as in terms of percentage relative to their initial as the brand number 1. We see that we're getting close to probably 90% with brand 1, but probably not quite, maybe about 70% of brand 2. So again, it's looking at the quality of your material as it's exposed, and then the shear rate is decreased. Again, you want your ketchup to pour out of the bottle to a high shear rate. We also want to rebuild once it's on your food. You don't want it to be pouring off and flowing off. Okay, another type of study is a creep recovery test, and this is the response to an applied stress and release. And the classic example, kind of keep in mind here, is squeezing and releasing a sponge. If you squeeze that sponge, does it come back to the same rheological properties as it did before? Also, twisting or compressing and then releasing a spring. So in this case, it's a binary type of study. You turn the stress on, and the stress goes off. How does the material respond? In the case of material A, we get a viscous creep. The compliance, which is 1 over stress in this case, increases, and then once that stress is released, it then falls back to pretty close to its initial level. However, with this material B, has a much higher level of compliance. However, once the stress is taken off, it does not recover nearly as much as material A. So we can quantify the elastic recovery as well as the loss of elasticity for that particular sample. Okay, we're going to switch gears here from rotational studies to oscillational studies. And this is kind of analogous to the agitator in a washing machine. And there's two ways to modulate oscillation. One is through amplitude and the other frequency. Very similar to AM and FM radio. AM is amplitude modulation, FM is frequency modulation. So focusing on amplitude modulation initially, it's a destructive test, and it's to determine the linear viscoelastic region of the material. In this case, we start at a low amplitude, low energy, increase the amplitude, and as we increase the amplitude, we're increasing the energy input. It basically determines the breaking point of the structure, which correlates pretty nicely with stability of the material. It can also be used to quantify stiffness, springiness, structural strength, and brittleness. We'll switch gears to frequency, which is assays which are not destructive. In this case, it measures the response to a material over the event time. Keep in mind that frequency is inversely proportional to time. So in this case, we are increasing or changing the frequency. In this case, we're going from high frequency to low frequency, and that's okay as long as you're within the linear viscoelastic region. You want to make sure that you're probing the structural properties of your material that are rheologically intact, and being below the linear viscoelastic region ensures that. So more focus on amplitude sweep. So again, we're increasing the amplitude or the energy until we break this down, the macrostructure. So I'm using a beer bottle as an example. I would not recommend putting a beer bottle between your plates and your rheometer, but it works as a really good example. So in this case, we're looking at the log of the elastic modulus, or G prime. This is the solid nature of the material. We'll talk more about G prime and some other parameters in a few minutes here. So basically, we're increasing the strain on the material or the stress, and we are evaluating or measuring the intactness of the material. And once we see that there's about 5% loss in the G prime, the elastic modulus, or the solid nature, we can see that starting to fail. And then we see the macrostructure destroyed, broken bottle. So two things here. First of all, we need to determine this linear viscoelastic region, or the upper limit, as an input for any subsequent frequency study. Because anything beyond this, the sample is destroyed. So typically, I like to, for a frequency sweep, I like to, once we know the linear viscoelastic region upper limit, I like to do an input percent strain somewhere around 40 to 60% of whatever the linear viscoelastic limit was. It's also important, since these are typically in log-log or log-linear plots, trying to visually determine a 5% loss is really not recommended. You really need to go look at the data table and see where is that consistent 5% loss of G prime occurring. Okay, we're going to switch over to a frequency sweep. In this case, we're using silly putty, which I imagine many of us had when we were kids, and maybe you still have some. No. So anyway, with the frequency sweep, we use that to probe the properties across the time domain. Keep in mind, frequency is inversely proportional to time. This is an assay that generates a unique rheological fingerprint or spectrum of the sample, and it uses the percent strain that was determined from the amplitude sweep. Again, it's that linear viscoelastic region. That's the upper limit, so you need to be well below that. So let's look at silly putty, the rheology of silly putty. So in this case, if you take silly putty, roll into a ball, leave it on a table, come back a few minutes later, you will see that it's changed shape. It is flowing. It's acting like a liquid. Sitting on a table is a low frequency event, a long time scale. And so as we start as a low frequency, you can see that the G double prime, which is the viscous modulus, or it describes the liquid nature, is dominant over the solid nature, the G prime. This is the red line. However, as we increase the frequency, at some point, a crossover point, the elastic modulus, or solid nature, becomes dominant, whereas the liquid nature is no longer dominant. So we now are working more with a solid than we were with the liquid earlier. And we can see if we take, and this is exemplified by taking the same silly putty, rolling into a ball, and letting it drop on the table. That silly putty will bounce. That event of hitting the table is a high frequency event. It's a short time scale. And silly putty is acting as a physioelastic solid at high frequency. Another way of evaluating the nature of the material is by the phase angle. And we'll talk about what that really means in a few minutes. With the phase angle, as we go, in this case, low frequency, the phase angle is greater than 45. The highest you can go is 90 degrees. The more towards 90 degrees you go, the more liquid it is. As in this case, as we're increasing the frequency, the phase angle is going well below 45 degrees. And anything from 45 as we go down more towards zero becomes increasingly solid. In this case, the silly putty at high frequency becomes increasingly solid, and that's also shown by its ability to bounce when it's dropped on the table. Okay, so this is the most math intense slide of all of them. I'm not going to go into all the details. So the frequency sweep outputs, the basic outputs are G prime, elastic modulus, G double prime, viscous modulus or loss modulus, which is the liquid nature of the material, and the phase angle is expressed in degrees. As I said, it becomes increasingly solid as you go from 45 to 0 degrees phase angle, and increasingly liquid as you go from 45 to 90 degrees. So what's going on here is this is oscillational type study. So we're exposing the sample to an oscillation, back-forth oscillation. And shown here is the sine wave. The red is the input stress from the plate, the upper plate going back and forth. The blue line is the measured strain. That's the response of the sample to that oscillation. You can see that there is a delay in the phase, and that is the phase angle. A perfect solid will have a zero out of phase angle, and so these will perfectly align. With a perfect liquid will be 90 degrees out of phase. And I am not going to go through the math. This is not the intent of this webinar. Some other outputs from a frequency sweep are B star and eta star. These are complex modulus and complex viscosity values. And basically, if you take just make a triangle where G prime is the x-axis and G double prime, the viscous modulus, is the y-axis. The complex modulus is a combination of these values. And the phase angle could be easily represented as the angle between G prime and the complex modulus G star. And this is just the ratio of the maximum stress over the maximum strain. And the important concept here is this complex modulus is a function of stiffness. The complex viscosity is just a complex modulus over the angular frequency. And this actually does correlate pretty well with the viscosity that would be determined from a rotational mode. Okay, I'm going to switch back to amplitude sweep because now that we have a better understanding of complex modulus and phase angle, I want to show you how amplitude sweep can be used to quantify texture and to better evaluate and compare various types of samples. So this is a plot of the complex modulus versus phase angle of a number of common products. And we can see that as a high phase angle, high complex modulus represents high level stiffness. Low complex modulus is a low stiffness. And we can go out to the phase angle is more liquid, less springy, less elastic. So in this case, we see butter is much more stiff than butter at 25 degrees. So we can see how samples can compare and cluster here. Okay, frequency sweep can also be used as a sensory measurement. In this case, this is a particular study using a sensory lab where they were evaluating yogurt, this regular yogurt with different amounts of fat and Greek style yogurt with different types of fat. They're just evaluating some kind of sensory parameter. So in this case, the rheometer values for this is the elastic modulus. You can see that the values for the rheometer and the columns correlated pretty well with what the sensory panel came up with. oscillation studies and using a temperature sweep can also be very helpful. This could be done in rotational mode too. But again, complex modulus is a function proportional to stiffness. Using butter here, two different kinds of butter. One was designed to be more spreadable than the other butter by adding some fats and oils. In this case, as we go from refrigerator temperature to room temperature, the butter with the added oils and fats was more spreadable, and that's demonstrated by having a lower complex modulus. It's less stiff. Another application of temperature sweep is demonstrating if your sample is rheologically stable as the temperature is cycled as you go up and down sweeps. And this is important in manufacturing and also to how does your product behave as it's exposed to high temperature and low temperatures, and is it reversible or irreversible? In this sample, we initially have a sample that has a very low D prime or solid nature about it. However, as it's heated, that greatly increases because we're looking at a log scale here, and then it's cooled. So this is a very different material now. However, if we heat it again and cool it again, we see that now we have a rheologically thermally stable material. It's very different from what we started with. The last assay is the pull weight study, and this models stickiness, tackiness, adhesion, cohesion. And basically, the top plate will compress the sample, and you can let it sit for a while if you need to rest, have it equilibrate, and then you pull the upper plate at whatever rate and force you determine. And the three measurements or three outputs from this kind of study is you can quantitate the area under the curve, usually after about 2 seconds, unless it's a very stringy type material. You can also report the time to achieve a 90% force induction. So basically, you're truncating the curve at this point, and you're now looking at this tail portion. And also you report the maximum force that was required to pull it away. So this is, so if we're looking at an overlay to trying to compare samples, the sample with the higher force makes sense, it's more sticky. The sample with the lower force is less sticky. Okay, getting back to the questions when we first started. So which is more viscous, honey or mayonnaise? Just want to warn you, you got to be careful about this particular one. Which is silly putty, a viscoelastic solid or liquid? Okay, so honey or mayonnaise. So we take mayonnaise, we put it on the plate. It doesn't, as it's sitting on the plate, a low frequency event, low shear event, it doesn't really move a whole lot. Whereas honey will tend to spread and smooth. So, but we need to be careful here because the measurement of viscosity depends on the shear rate. Mayonnaise will shear thin. So if we measure viscosity at a low shear rate around 2 reciprocal seconds, it's not really all that low. I often go down to the low milli reciprocal seconds. We can see that has a much higher viscosity than honey. Again, this is on a log scale. However, if we were to do that measurement at 40 reciprocal seconds, which is not all that high, we can see that honey is much more viscous than mayonnaise. Mayonnaise shear thin, honey does not. And yes, this is me harvesting some honey in our backyard. So there's actually some honey work that I did with honey I collected from the back. Anyway, back to silly putty. And I know this is a repeat of what I've gone through before, but I just want to review some aspects of frequency study. In this case, we can see at a low frequency, the elastic modulus d double prime is higher than the d prime, the elastic modulus. It's viscous dominant, it's more liquid at low frequency, as well as the phase angle is well over 45 degrees. We can see it's about 85, 80, or in high 80s here degrees. It is liquid dominant. As we increase the frequency, it becomes more solid dominant. So the question is silly putty a viscoelastic solid or liquid at rest? It's a liquid. So you can amaze your friends at next gathering. So in conclusion, which test is better? It depends on the question to be answered. You need to be mindful of the experimental details, such as handling. What geometry do we use? What size geometry? What is the gap between the plates? And also, what does the sample change over the assay time? A viscometer is a very good basic QC tool. Again, it's just giving you a single number under well-defined conditions: spindle type, speed, temperature. A rheometer characterizes a sample in more detail. With rotation, we look at some examples of flow curve, non-equilibrium, shear stress, and that models spreadability and pumpability, whether or not a suspension may cause a settling over time. We look at equilibrium viscosity, shear rate steps. Viscosity, we look at the rebuilding of catch-up after shear thinning. The creep test is response after release to stress. Is it coming back to its same rheological properties? An example of that was that sponge and spring, as well as the temperature sweep. And the oscillation mode, we looked at amplitude sweep to define the linear viscoelastic region or the breaking point, and that correlates with stability and texture. Then we moved on to the frequency sweep, which is that rheological fingerprint across time. We looked at the G prime, G double prime, phase angle, complex modulus, and complex viscosity is the output. Again, classic example here is silly putty. As well as we looked at temperature sweep. So we're getting reversible or irreversible rheological changes as we change temperature over time. And the example of that was the butter and that and generating a more stable material. And we also talked about the vertical or pull-away study to correlate with stickiness. And with that, I thank you for your time, and I'll be happy to answer some questions.
Thank you, Mark. That was a great webinar and very thorough and complete. I'll just remind everyone that since you are muted, if you can please write any questions you might have for Mark into the chat box on the right-hand side of your screen, we can get those answered for you. Okay, so we have a question, and I'll read it out. If we take your hand cream slide as an example, how do you use a rheometer in a product design stage to know the different viscosities? That is, hand cream in a packaging compared to a hand cream during application in hand.
Sure, thank you. That's a good question. The sample sitting in a package is experiencing a very different shear rate than the sample that's being applied to your hands. The shear rate at storage is in the low milli to micro reciprocal seconds, and putting something on your hand could be 10 to 100 reciprocal seconds. And a rheometer is very well suited to quantitate that. That's just doing the second study we talked about. That's the step or equilibrium viscosity study, where we can put in the whole range of shear rates going from very low up to very high, and we can see how that sample changes as a function of changing, or in this case, increasing the shear rate. So you can tell if the sample is really thick to begin with, say in the jar, does it scoop well, does it pump well, and we can get a sense of how does it feel when it's applied on the skin. Is it hard to start spreading, such as Vaseline? That's very hard to start spreading. It doesn't feel very good. Whereas you take some other kind of skin products, they feel nice and smooth. There's a whole different shear rate, shear thinning process, and yield stress and yield viscosity associated with those processes.
Thank you. And another question. Is there a single general instrument to address most studies? What are the must-have capabilities?
Okay, yeah, good question. I think it depends on the question you're trying to answer. And if I had to give you an answer for one, I would say it would be a rotational rheometer. And let's see if I could go back. It's in the backup slide. So if we go to some of the earliest slides, so this slide, we can see as we're looking at, again, it depends on the question you're trying to answer, but if it's a classic viscometer, it's a very good instrument, but it has a relatively narrow range. However, a rotational rheometer such as the Malvern Connexus, and TA makes one, and Tom Parr makes it. They all make very good rheometers. They have a much broader range of shear rates or shear stresses. If you really need to go up to very high shear rate or shear stress range, you should be looking at a capillary rheometer. But really, if you're just looking for general rheology for common materials, semi-solids, and so on, the rotational rheometer should do the job. And what are the must-have capabilities? Again, it depends on the question you're trying to answer. Any rheometer will give you the rotational and the oscillational capabilities. I would make sure that you have a good array of geometries in terms of plates and cones. And we also provide that services at Rheology testing services. We can provide all these studies we routinely do. So capabilities, you really want to have something that can go down to a very low shear rate, at least down to 1/1000th of a reciprocal second, and also go up to very high shear rates. So again, the rotational rheometer should meet your needs pretty well.
Okay. And another question, what is your recommendation for sample handling of pork trimmed fat? Is it better to be pre-ground first?
For what kind of trans fat was that, Amy?
I'm sorry, pork trimmed fat. What is your recommendation for sample handling of pork trimmed fat? Is it better to be pre-ground first?
I think that we really need to have the data to tell us that answer, because it depends on the properties of the material. I would really do a study. It's not hard to do these studies. If you have the equipment and the experience, I would look at the ground and unground and grounded materials first, because there's certainly going to be a difference. I can promise you that, and they're going to require some different experimental strategies. It depends on what the end product is. What's the question you're trying to answer to meet your business needs? If it's a material that the product will be ground, I would look at I would probably use, with something like that, it's a relatively soft material. I would use probably a flat plate, and let's see. I would, in terms of gapping, you may want to. We want to experiment with. Do you want to gap a particular gap thickness, say 1 millimeter, or do you want to place a certain force on it? I would probably think with that kind of material, you want to go with a particular force, because it's kind of like a polymeric. Some of the bioengineered polymeric materials we've looked at, they can tend to differ greatly by the thickness. So.
Thank you. And another question. If a viscometer is used to measure formulation quality in production, how can we use data from rheometer studies to establish good viscosity targets? What if formulation tends to shift in viscosity over time?
That is a classic question. And that's where I was highlighting that a viscometer will give you a viscosity value given with the defined spindle type, the spindle speed, and the temperature. So if I understand the question properly, you're asking, well, how do the values from a rheometer and a viscometer correlate? Sometimes they don't, and because you're really looking at different processes. You're looking at often the sample immersed in say the viscometer geometry is immersed in the sample, whereas the rheometer is applying a different type of force throughout the sample. Sometimes they do. And a lot of times, if you want to do that, you just need to tweak the parameters of either the viscometer or the rheometer to see if they can match. And that could be the plate type, the plate speeds, the force, the height of the sample, and so on. So, with some work, you might be able to get some good correlation with that, but it really depends on the sample and being very careful about your experimental considerations.
Excellent. Are there any other questions for Mark? I'll give everybody another second as I thank you, Mark, so much for your presentation, as well as willingness to answer questions and share such a good overview. And I also thank everyone for joining us.
So, Amy, I was just looking at the last part of that question, if I have time. What if the formulation tends to...
Absolutely.
Thanks. What if the formulation tends to shift in viscosity over time? That's a very important question, and that's something. It depends on what conditions and over how long a time, and if that's an issue. Yes, formulations can definitely shift over time. You need to see is there phase separation occurring. You also need to see if evaluate if there's sedimentation and so on. So yes, that is a very common situation, and that's why rheology is so helpful to look at time points of your sample. And that's a critical thing that I was involved with at Stiefel, just looking at samples stored at various conditions over various times and seeing indeed that the rheology properties change.
And it does look like another question has come in. How would you most accurately prepare and measure, and I don't know how to say this word, sorry, I'm a marketing person, viscoelastic properties of butter at 5 degrees C, pretty solid, in terms of gap height, gap positioning, height or force?
Sure, you did a great job on viscoelastic, Amy.
All right.
So certainly with a rheometer, you would set that. You could easily set the temperature at 5 degrees. That's a standard assay temperature, and it is pretty solid. In terms of gap height and positioning, it depends on if you're viscoelastic. You're looking at an oscillation type measurement. I would think somewhere, maybe somewhere between the 0.2 to 1 millimeter would be reasonable. And then in terms of gap positioning, height or force, it depends on the properties. And the reason I say that is just in the gapping of that butter at 5 degrees, you can maybe get some fracturing of that butter to occur. And so you may want to see if you want to condition that butter, maybe take it up to a higher temperature or gap it at 5 or 25 degrees, and then cool the plate down to 5 degrees. I would probably use, in that case, I would maybe go with, I think they're probably for butter pretty similar. Certainly the data will tell you. I think that maybe going with a height would probably be the most straightforward. So, between 0.2 and 1 millimeter would be fine. But it certainly would not be bad to look at gapping your butter at 5 degrees using different forces. Go down to a fraction of a newton up to, at least with the Malvern connections, up to 40 newtons. So that'd be an interesting study to do.
Okay. Well, I think we are at the end of our time. Great questions. And thank you, everyone, for joining us. And thank you, Mark, for your presentation.
Okay, well, I thank everybody. And feel free to send me an email at rheologytestingservices@gmail.com.
Oh, it does look like, though, we do have another question that came in, and Mark, do you have time? I know we're at 1, but if we can help. Okay. Can temperature control at the bottom plate ensure temperature uniformity through the sample? Because some structured fat samples are sensitive to temperature change.
Okay, yeah, that's a good question. So what I would recommend in this case, and it depends on the temperature that you're performing our assay with. Certainly, you want to make sure that you have a thermal covers over your sample, over your plate. The other thing I would suggest is that you just do a time study. And yes, the upper plate is not temperature controlled. And so you can just take that particular sample, and my standard temperature equilibration time is 5 minutes. So what you could do is do your measurement at 5 minutes, and then or 5 minutes temperature equilibration, and then maybe take it out to 10, 20, and then out to 60 minutes and see if your rheological properties change. And that's assuming your sample is not changing inherently over that time due to loss of volatiles or curing or something like that. That's a good question. The other thing, if that's a problem, you could put less sample on, and that would be by either using a smaller geometry or a smaller gap. Okay.
So since we are at the end, but I know we've had some great questions, and some folks may come up with questions as they kind of process this. So we will be sending you next week an email with the edited recording of the webinar, and I'll make sure in that email to put Mark's contact information so that you can follow up with him should you have further questions. So look out for that email.
Okay. And the website is simply rheologytestingservices.com.
Perfect. Okay, so we'll include all of that with your email recording so that you'll have everything you need in case you have more questions.
Okay,
so
great.
Thank you, everybody, and thank you, Mark, and have a wonderful rest of your day.
You too. Take care. Bye-bye.